Hey guys, and welcome back to another video. In this video, we'll be talking about the first derivative test. Alright, so let's get started. Alright, so to begin with, let's consider the graph of some function whose graph looks like this. Alright, and we'll call this point right here to be x equals c. Alright, so now let's see where is this function decreasing and increasing. So it's pretty obviously decreasing on the interval from negative infinity to c, right? So it's decreasing on the interval from negative infinity to c, and it's increasing on the interval from c to infinity, all right? So it's increasing on c to infinity. All right, that was pretty easy. All right, good. So now let's just consider some point x. So I'll call this point right here x to the left of c, all right? And let's just draw the tangent line to the graph of f at x. So it looks something like that, right? So what is the slope of this line? Well, yeah, it's negative, right? And so we know from previous videos that the slope of the tangent line is given by the derivative of f. So the slope of this tangent line is simply just equal to f prime of x. And we've determined that it's negative. So f prime of x is less than 0, all right? But in fact, this is true for all x less than c, right? So if we draw some other point right here and the tangent line to that, this slope is also negative, and then the slope at this, the tangent line at this is also negative slope, all right? And then furthermore, notice that as x approaches c from the left, right, as x is getting closer and closer to c, our slopes are becoming less and less negative, and they're approaching a zero slope, a horizontal tangent line, which has zero slope, which occurs at x equals c, all right? So when x is less than c, we have negative slopes. Our tangent lines have negative slope, and so that means that f prime of x is less than 0 for all x less than c. And then when x is equal to c, our slope of the tangent line is equal to 0. So f prime of x, or f prime of c, is just equal to 0 when x equals c, all right? Because you have a horizontal tangent line. And so now let's consider some point x greater than c, right? So if we draw the tangent line to this point, we have a positive slope now, all right? And again, this is true for all x greater than c. So if you draw the tangent line to this point, it also has positive slope, and similarly, the tangent line to this point also has positive slope. So therefore, for x greater than c, f prime of x is greater than 0. Our derivative is positive, right? And so then I want you to notice one thing, is that when x is less than c, our derivative is negative, right? But when x is less than c, that's the exact same interval where our function is decreasing. All right, so it seems as if negative derivatives correspond with decreasing functions. And indeed, that is the case. So that's the first point I want to make, is that if f prime of x is less than 0, then that means f is decreasing at x. All right, and then similarly, we have f prime of x is positive for all x greater than c, and that's the exact same interval over which this function is increasing. So if our derivative, if f prime of x is positive, that means that our function f is increasing at c. Increasing at x, all right? So in this way, the first derivative tells you where a function is increasing or decreasing, all right? And then finally, another thing I want to point out is that, so it's pretty obvious that our function f has a minimum at x equals c, right? I'm sure we can all agree on that. So f of c is a minimum value for our function, all right? And so let's see what the behavior of the derivative is as x crosses c, right? So for x less than c, our derivative is negative, and then as soon as x crosses c and becomes greater than c, our derivative becomes positive. So therefore, it seems as if, so our derivative f prime of x is going from negative to positive in this case, right? And so it seems as if a minimum value is denoted by the derivative going from negative to positive, right? So right now, this is just like a conjecture. We don't know for sure yet, but this is like our observation, right? So now let's consider another graph. So I'm gonna erase this real quick. Whose graph? So now let's consider another graph that has a maximum value, right? So now again you have x equals c, but now this time, so this is the graph of y equals f of x. So now this time f of c is a maximum value, right? F of c is a maximum value. And so now let's consider what happens to the derivative as x crosses c. So when x is less than c, we have the tangent line has positive slope, right? So our derivative f prime of x starts off positive, and then as we cross c and now x is greater than c, now the tangent lines all have negative slope. So now our derivative goes from positive to negative, right? And then obviously at x equals c, our derivative is 0 because we have a maximum there. So now it seems as if the derivative going from positive to negative signifies or denotes a maximum value of our function f. All right. So these are just like theories, just like conjectures for now. But at least now we have like an intuition, a geometrical sense of why this maybe could make sense. All right. Good. And so now let me write out the full statement of the first derivative test. So the first derivative test basically confirms our results, right? So it says that indeed, if f prime of x goes from a negative value to a positive value, then f has a minimum value somewhere in between. And then similarly, if the derivative goes from a positive to a negative value, then our function has a maximum value somewhere in that interval, right? So that's basically all the first derivative test says. But I'll write it out for you guys and its formal definition, formal statement. All right. So the first derivative test. All right. So the first derivative test basically says like, if f is a continuous function on the interval a to b, right? Open interval a to b, then so you have two cases, right? So if the derivative f prime goes from negative to positive, that means that you have a minimum value. So that means that f has a min value somewhere in between this interval. And then the second case is if f prime goes from a positive to negative value, then that means that f has a max value. All right. And again, like the intuition for this, we just saw in the previous example, is just like the slopes of the tangent lines, right? And so another important thing is that the first derivative test can only help us find local extrema, right? So what does that mean? What is local extrema? Well, so like suppose you have the graph of some function, and its graph looks like this, right? So at this point and this point, so I'll call this C1 and we'll call this C2, right? So the slope of the tangent line right here is a horizontal tangent line, so the slope is 0, right? And similarly right here, slope of the tangent line is 0. And so that means that the derivative of this function, so if we call this to be, let's just say g of x, right? This means that g prime of c1 equals 0, and we know that g prime of c2 equals 0, right? Because the slope of the tangent line at those 2 points is 0. But this means that c1 and c2 are critical numbers, right? So therefore, our function g, as we can see from the graph, has a local maximum at C1 and a local minimum at C2. And the reason we call it a local minimum max and not a global is because eventually, so like for x greater than C2, our graph goes above our local maximum here. So like the this maximum is not a maximum over the whole domain of G. Eventually, G does exceed this value. and similarly, some g does go below this minimum value. It's only a maximum value locally. It's only like a maximum value near all the other points, and similarly, this is only a minimum value near the other points in its kind of like range. All right, and yeah, so basically the first derivative test only gives us local extrema. All right, so now let's move on to some examples. All right, so this is our first example. So we want to find the intervals where this function is increasing or decreasing, and then we want to find any local extrema of the function. All right, cool. So the first step is we should just say the derivative of a function f, right? Because in order to find where the function is increasing and decreasing and to find any local extrema, the derivative is going to be super useful. All right, so let's go ahead and differentiate f. So f prime of x is equal to 6x squared plus 6x minus 12 by the power rule, right? And so let's go ahead and set this equal to 0 to find any critical points of our function, right? So if we go ahead and solve this for x, you should get that. So first of all, we can divide both sides of this equation by 6, right? So we get x squared plus x minus 2 equals 0. And then this factors as x plus 2 times x minus 1 equals 0. So therefore, our critical points are x equals -2 and 1. Right? So now, for these first derivative test problems, a very good strategy is to go ahead and draw a numbered line and then put down all your critical points that you have. So we have -2 and 1 in this case. And this is going to be our f prime of x values, right? So basically what we're going to do is we're going to evaluate f prime at values less than -2, in between -2 and 1, and then greater than 1. And really we just want to see what the sign of f prime is, because that can tell us whether the function is increasing and decreasing, and then it can also help us determine which type of extrema occurs at each of these critical points. All right, good. So if x is less than -2, then f prime of x is positive, right? And the way to find this is simply you can substitute any value of x less than -2. So for example, you can substitute in -3, right, into f prime of x, and you would get that you get like a positive number, all right? And then similarly, we can find some value of x between -2 and 1. So for these ones where it's like between a negative and a positive number, just put in 0, right? It's the easiest. So if you evaluate f prime of 0, clearly you get -12, so that's a negative number. And then for x greater than 1, so let's just say 2, you get a positive number out of f prime of x. All right, good. So let me go ahead and erase this, and let's see where our function is increasing and decreasing. So increasing, f is increasing wherever our derivative is positive. So our derivative is positive on the interval from -infinity to -2, right? And then union with the interval from 1 to infinity. So now let's see where our function is decreasing. So our function is decreasing wherever our derivative is negative. All right, so on our interval, in this case, from -2 to 1. All right, so this is where the function is increasing and decreasing. All right, so now let's go ahead and characterize our local extrema at these two critical points. So at x equals -2, our derivative goes from a positive slope, so like this, and then it's going to a negative slope, like that, right? So that means that at x equals -2, you have a maximum value, all right? And then at 1, our derivative is going from a negative value to a positive value. So at x equals -1, you have a minimum value, all right? Good. So now let's go ahead and find what those minimum and maximum values are. So like I said, f of -2 is a maximum value by the first derivative test. And f of -2 is equal to 20. So this is a maximum value. And then f of 1 is a minimum value, again by the first derivative test. And f of 1 is equal to -7. All right, so that's the answer. The function is increasing on this interval, decreasing on this interval, and then these are the maximum values. All right. All right, let's go ahead and do another example now. All right, so this is our next example. We have g of x equals 3x to the fifth minus 4. All right, so again, the question is the same, right? So let's go ahead and take the derivative of g. So g prime of x is simply equal to 15x to the fourth, right, by the power rule. And so now let's go ahead and set this equal to 0 to find the critical points of g. So setting this equal to 0, you simply get one solution, x equals 0. And so this is our only critical point because notice that g prime of x is not undefined anywhere, right? So the only critical points you get are from setting it equal to 0, and then the only critical point you got was x equals 0. All right, so this is our only critical point. So now let's go ahead and make our number line again. So in this case, we only have one critical point at 0. And so now we're evaluating g prime for x values that are negative and positive, right? Less than 0 and greater than 0. So if x is negative, a negative value to the fourth power is positive, right? And so then positive number times positive 15 is positive. So we have a positive derivative for x less than 0. And then if x is greater than 0, x to the fourth is still positive, and then times 15, that's still a positive number. Okay. But now notice something interesting here, right? As x crossed 0, the sign of our derivative didn't change. It remained positive. So what does that mean? It means that at x equals 0, you have neither a local minimum nor a local maximum, right? Because the first derivative test says you only have a local min or max if the derivative changes signs. So because the derivative did not change signs, x equals 0 is none of the above, right? It's neither a local min nor a local max. And then again, because the derivative is positive over its whole domain, that means that this function g is increasing over its whole domain. Okay, so this function is increasing over its whole domain, so over negative infinity to infinity. It's decreasing nowhere, so decreasing, I'll just say NA, not applicable. And then local min or max has none, so I'll just say no local extrema. And so then you might be wondering, how is that even possible? Well, let's go ahead and take a look at the graph G, right? So if you were to graph G, you would get a graph that looks something like this, right? And so at x equals 0, right here, notice the tangent line to this point is indeed horizontal. So therefore, the slope of the tangent line, the derivative at x equals 0, is 0. But is this a minimum or maximum value? Clearly not, right? So this is like an example of where critical points may not always yield local extrema. All right, good. All right, so now let's move on to our final example. All right, so our final example, we have h of x equals sine x over 1 plus cosine squared of x. All right, so again, like always, let's first take the derivative of h. So h prime of x is equal to, so we can just use the quotient rule right here, right? So we have low d high, so the derivative of sine is cosine x times 1 plus cosine squared minus sine x times the derivative of the bottom function, which is negative 2 cosine x sine x. All right, and then we divide everything by the square of 1 plus cosine squared. Okay, so let's go ahead and expand the numerator, and we can like combine like terms and then just simplify it. All right, so we get cosine x plus cosine cubed x plus 2 cosine x sine squared x all over 1 plus cosine squared x quantity squared. So I want to get rid of this sine squared and express it in terms of cosine, right? Just because that way we can get everything in cosines and it'll be nice. So if we remember from pre-calculus, and if you don't know this identity, then you can check out the pre-calculus series on this channel. I cover everything from basic functions all the way to trigonometric identities and solving the equations. So I definitely recommend you check that out. But if you remember from pre-calc, sine squared of x that is equal to 1 minus cosine squared of x, right? And this is from the Pythagorean identity. So let's go ahead and substitute this value in for sine squared of x and see what we get. All right. All right, so I have substituted in 1 minus cosine squared x for sine squared of x. All right, so now let's go ahead and simplify h prime of x. So we have h prime of x is equal to cosine x plus cosine cubed. And then we could distribute this to cosine x. So we have plus 2 cosine x minus 2 cosine cubed x all over 1 plus cosine squared. All right, and so then notice that things in the numerator can simplify out. So let's go ahead and do that. So we have cosine plus 2 cosine, so that's 3 cosine x. And then we have cosine cubed minus 2 cosine cubed, so that's minus cosine cubed x all over 1 plus cosine squared x, and then whole thing squared. All right, so now we have to find the critical points of h. Let's go ahead and set this equal to 0. And so then notice that this expression is only equal to 0 when the numerator is equal to 0. All right, so we have 3 cosine x minus cosine cubed x equals 0. All right, so we could factor out a cosine to get cosine x times 3 minus cosine squared x equals 0. And so then from here you get two options, right? So either cosine x is equal to 0, or we have 3 minus cosine squared is equal to 0, which just means that cosine squared x is equal to 3. All right. But then notice something, right? Because cosine x is bounded between -1 and 1. So therefore cosine squared is also bounded between -1 and 1. So therefore cosine squared x equals 3. That's impossible, right? Because the maximum value cosine squared of x is 1. So therefore this case right here has no real solutions. All right. So I'll just say no real solutions. All right. So then now we're only left with cosine x equals 0. And this occurs at x equals pi over 2. And then we have integer multiples of pi. All right, so pi over 2 plus n by, where n is an integer. But then notice that this means that cosine x has infinitely many solutions. And so that means that we have infinitely many critical points. And technically that does make sense, right? Because we have sine x over 1 plus cosine squared. So that's like a periodic, that's like a sinusoidal wave. And so therefore you have infinitely many local max and infinitely many local min. But just to make like the math easier and like finite, let's go ahead and restrict our graph on the interval from 0 to 2 pi. All right, because the period of this function is 0 to 2 pi. So therefore, everything that occurs on 0 to 2 pi can just be replicated throughout. All right, so then therefore, on this interval 0 to 2 pi, our critical points now become x equals pi over 2 and then 3 pi over 2. So these are our critical numbers. All right, good. And then furthermore, notice that h prime of x is never undefined because the denominator is always strictly greater than 0. So therefore, it's never undefined. So the only critical points we get are from setting it equal to 0, which are pi over 2, 3 pi over 2. All right. So now let's go ahead and make our number line. Okay, so over here we have our number line. So I plotted our critical points, pi over 2 and 3 pi over 2. And then notice that I also plotted the points 0 and 2 pi just because we restricted ourselves to that interval. All right. So now let's go ahead and test x values in each one of these intervals. So I'll just tell you, so if you test some x value in 0 to 2 pi, you get that h prime of x is positive, okay? And from pi over 2 to 3 pi over 2, in that interval, h prime of x is negative. And then from 3 pi over 2 to 2 pi, h prime of x is again positive. All right? Good. So now let's go ahead and see where this function is increasing or decreasing. So this function is increasing wherever the derivative is positive. So therefore, on 0 to 2 pi, or sorry, on 0 to pi over 2, as well as 3 pi over 2 to 2 pi. Okay? And then it's decreasing wherever the derivative is negative. So in this case, from pi over 2 to 3 pi over 2. All right, good. So now let's go ahead and see what type of local extrema we have at pi over 2 and 3 pi over 2. So at pi over 2, our derivative is going from positive to negative, right? So that means that by the first derivative test, at pi over 2, we have a local maximum. And then at 3 pi over 2, our derivative is going from a negative value to a positive value, so therefore we have a local minimum at 3 pi over 2. All right, so now let's go ahead and find those min and max values. So h of pi over 2, this is equal to 1, and so that is a local max, right? And then h of 3 pi over 2 is negative 1. That's a local min. All right, so there you have it. All right, that pretty much wraps up this video on the first derivative test. If you found this video helpful, please make sure to leave a like and don't forget to subscribe. I'll see you guys in the next video.